Now that it's warmed up a little bit, I just wanted to finish off today's session by adding a few details to some of the points that I was talking about earlier on when we were discussing glacier sliding. One of the points I want to make is just to get you to think about how you can predict the amount of glacier sliding you'd expect, other things being equal, simply developing on from those ideas you were playing with earlier on about Glen's flow law and the shear stress equation. So if we're saying that the driving force behind sliding is shear stress, both locally derived shear stress that you can calculate from the overburden pressure on the surface gradient, but also some component of longitudinal stress from movement further upstream in the glacier, we can begin to predict how much sliding we'll have at the bed if we can calculate tau b, the basal shear stress at each position around the bed of the glacier. So if we imagine a theoretical ice sheet profile, so this could be half of the Greenland ice sheet, say, in the summit of the ice sheet we have a flat surface, therefore the basal shear stress tau equals rho gh sine alpha, alpha is 0, therefore the basal shear stress is going to be 0. So if we draw onto this a graph of basal shear stress, at this point basal shear stress 0. As we move out towards the edge of the glacier, we start getting some gradient here. So there's a non-zero gradient and there's an ice thickness, so we begin to get some shear stress. Now as we move on, the thickness is decreasing, but the gradient is steadily increasing. By the time we get to the edge of the glacier, the gradient is steeper, but there's here h equals 0. There's no ice thickness. So again, the basal shear stress at this location, let's draw it in red, the basal shear stress is 0 here, begins to increase here, comes back down to 0 there, and there's going to be a shape something like this, where there's a peak in the basal shear stress at some point in between this 0 location and this 0 location. Some people argue that that peak is likely to be somewhere around the equilibrium line, but certainly you would predict a peak in basal shear stress and therefore, other things being equal, a peak in the basal sliding rate. The second thing that I wanted to just add a little bit more detail to, or just get you to think a little bit more about, was regulation. And I was talking previously about a situation where there's a high pressure zone on the upstream side of an obstacle, and that can cause local melting because of the pressure increase. The lower pressure on the downstream side results in refreezing, and so we have movement of water and ice around the obstacle, and so by regulation the ice can overcome the obstacle. But I was talking about the fact that this can draw heat from the surroundings in order to support that melting. Even though it's driven by a pressure change, not a temperature change, it requires energy to make that phase change, and so would reduce the heat in the surrounding area, and that can cause the regulation process to stall if we don't have sufficient energy being resupplied from this release of heat, from the release of heat on the downstream side. In that situation, what happens is that the process seizes up for a bit because of the reduction in temperature here, meaning that we're too cold now for the pressure increase to actually lead to any melting. And then gradually, as heat is resupplied, we get back to a position where movement can happen again, and we get back to regulation occurring. So there are periods of regulation slip occurring, and then periods when it's all seized up because of the cooling where it isn't occurring. And I didn't mention in the previous bit of video that I showed you this label that's often applied to that, which is stick-slip motion. So when you encounter that in your reading, that's what we're talking about. That's what we were talking about earlier. I think I called it stop-start in the regulation process. At the time I should have used, and the conventional term for that is stick-slip motion, which would result in occasional movements of the glacier by regulation, interrupted by periods when movement isn't happening. And if you look at papers such as, for example, the Camel La Chapelle 1964 is one of the classic papers where this kind of motion is observed and described. A final thing I want to say just a little bit about is friction at the bed during sliding. We're talking about driving forces, the stress which is making sliding happen. I've referred briefly to friction or resisting forces. I just wanted to say a little bit more about that and particularly draw your attention to the role of water pressure in that. There are all sorts of different equations that you might see for friction at the bed of the glacier. I know you don't want too many equations in this module. I said there wouldn't be many. But this relationship is quite an important one for you to recognise. And friction is sometimes given as a shape factor or a roughness factor. So this is just a number that increases as we have rougher and rougher surfaces. So we're going to multiply our term by a small amount if it's a smooth surface and by a big amount if it's a rough surface. So it's a fairly obvious way of running an equation. You're talking about friction. Well, the rougher it is, the more friction there is, so we'll have a roughness factor and we'll increase that number for rougher situations. But we'll multiply that, or that will be multiplying up against this term, rho GH minus PW. Rho GH you're familiar with, you know that. That's the density, the force of gravity, the thickness. So that's the weight of the glacier that we've used before. So I don't feel as if I'm giving you a new equation here because it's the same old stuff. So the friction is just how rough the bed is multiplied by the weight of the glacier. Heavier glacier, you can imagine it's more that weight and that roughness, it's more going to need more effort to move that, so weight is an important factor in determining the friction. But weight can be compensated by water pressure of water at the bed. If you have high basal water pressure, if there's water being pumped and squeezed and stored at the bed, I referred previously to lubrication, but if we have high basal water pressure, that will compensate for the overburden pressure of the ice. And you'll see sometimes in your reading people referring to not just the overburden pressure, but the effective overburden pressure. And what they mean by that is that it's the overburden, the weight of the ice, but minus, compensated by any water pressure. So N, the effective pressure, is rho GH minus PWP. So the friction that's opposing our sliding is to do with the roughness of the bed and the effective overburden pressure, which is overburden pressure minus water pressure. So we've talked a little bit about glacier movement, and we've talked so far about internal deformation or creep and basal sliding, and hopefully you've begun to recognise that some of the same factors are important in both of those kinds of movement. We're interested in basal shear stress, we're interested in resistance in terms of friction at the bed of the glacier, we're interested in the shear stress all the way through the thickness of the glacier and the resistance to deformation from factors such as the hardness parameter, the temperature dependent hardness parameter in Glen's flow law. So there are all these different factors floating around here: the water pressure, the temperature, the driving stress, the friction, the amount of debris in the basal ice which is going to be controlling the friction. There are a number of different factors floating around in here that you're beginning to see are all important in controlling these different kinds of motion. So what we need to do next is move on to the third style of motion that I said we'd be talking about, which is subglacial deformation. And Rich is going to come in next week and give you some information about subglacial deformation that will then roll into our understanding of glacier motion overall, and we're then going to take those different styles of motion and apply all of them to try to begin understanding why glaciers not only move the way they do, but why they have the overall shape that they do. Because the shape of a glacier, the morphology of a glacier, is very much connected to the movement of a glacier. And glacier dynamics and glacier morphology are really important things for you to be able to tie together. And that's what we'll be moving on to at the end of next week, after we've had a bit of a conversation about subglacial deformation at the start of next week.